process of this test into 3 stages. Have you any idea what's the difference between these 3 stages?
In the two first stage, the moment increase, but in the first stage, we don't have the moment is 0.
The moment is 0.
Okay, the shear force in the middle is 0.
The shear force in the middle is 0.
And the bending moment is
constant.
Yeah, it's constant. But in the side, the shear force is there, it's constant.
Yeah. So for this test, according to the result, we have divided into these 3 phases. First one is working without crack, second one working with crack, the third one is failure phase. So when an idea, see this figure. And the first stage, second stage, crack gathering appear, and then the third stage, the speed will destroy. So for this 3 stages, this figure describes the distribution of the stress and the stress for the compressive stress or tensile stress distribution on this section. So can you describe the whole process? How the stress distribution changed with the test going on or with the load increase?
How the stress distribution?
Yeah, or see, compared with the RA and the 2, what's the difference from these 2 stages?
The height of the crack is increasing. And the shear force in that downstairs is going.
This is not the shear force actually.
The distance from the distance.
Which distance?
From the normal, is it the normal force? The middle one. It keeps increasing. If it keeps increasing, meaning like how do I say it? The strength keeps also
the crack increase.
And meaning it's getting to the 8 yielding point. So the stress at the top part is also increasing.
So compared with these 2,
comparing, meaning here the cracks are like.
So once the crack appear, what happened?
The
strength
steel or reach its fellow.
Yeah, yielding point.
Yielding strength.
Yeah,
At the beginning, when the crack appear, the steel have not reached its yield strength.
Yeah.
Actually, at the end of the second phase, it's reached the yield strength. But at the beginning here, when the crack just appear, you see, at the end of the first phase, the up part of the section is in compression.
Yeah.
The lower part is in tension. So not only the steel bar, but also the concrete bearing the tensile force. Once the crack appear, the tensile force induced, or the tensile force bearing by the concrete was transferred to the steel. So the lower part of the section no longer bearing the tensile force of the concrete. All the tensile force was bearing by this steel or the reinforcement. That means the stress of the reinforcement increased greatly. And also you should see the neutral x compared to this is going up a little bit.
Yeah.
But at this stage, the biggest change is the stress of the reinforcement increased greatly.
Yeah.
And with a little improve or going up of the neutral x. And then the second end of the second phase, with the pressure increase, correct? The width, the length increase, generally the reinforcement reaches the yield strength. And you see the distribution of the compression stress is no longer in straight line distribution. It's in a curve distribution.
Yes.
So at this end of the phase 2, the reinforcement is reaching its yield strength. And then with the load increase, so what's the difference of this? The phase 2, end of phase 2 and the beginning of phase 3, what's the difference with this?
Yeah, the load has become more, so the stress is also rising.
So which stress? Tensile stress or
Yeah.
compression stress?
Tensile.
Tensile stress. Tensile stress is a
No. Compressive stress.
compressive stress.
Yeah, the compressive stress.
So at this stage, because the steel or the reinforcement have reached the yield strength, the stress will not increase, nearly keep unchanged, but the strain will increase greatly. That means we need to keep this structure keep balance, but this force now it does increase. We have to increase the arm of this force. Then the neutral x, see, compared with this, the neutral x keep on going up. Keep on going up, and then the compressed stress increases greatly. This is the beginning of the phase 3. At the end of the phase 3, see what's the difference in these two stages?
It's a stretch. The compressive stress, the stress side has stretched, like extended the curve.
It reached the failure process, the failure stage.
Yeah. Like it's the point where the thing has collapsed, like destroyed.
Yeah. At the end of this phase 3, because the reinforcement already reached the yield strength, the concrete at the end of phase 3 also reached the compression strength. That means the concrete was crashed. So compared with these two figures, you see, at the beginning, still the distance to the neutral, the longest one, the strain is larger. But at the end, actually the largest stress is not the top. It's a little bit going down. Yeah, that's why, because the top already crashed. So that's the total process of this test. This 3 phase is from this 3 phase. I think we have finished to here. 70 is here, should be here. the film. So this is the reworker phase of this section. The first point, RA point, can be used as a base for calculating crack capacity of the flexion member. So what's the meaning of this is? Because at the end of the phase 1, the crack have not appeared. It's going to appear once the tensile force reach the tensile strength of the concrete. The concrete will crack. So RE point, that means the end of the first stage. We can use this point as the base to calculating the crack capacity. So that means when the crack is going to appear, if you want this beam working without the crack, then you can use this point to control it. So under how much tensile force the beam will not generate crack or working with no crack. So then you know from this point you know. Once the tensile force is larger than this point, the concrete will crack. So the phase 2 is used as a base for deformation and crack propagation over surface time. So that means for this phase 2 you can check the crack or deformation if the crack is too large or deformation is too large, because for the surface time we can allow the beam working with the crack and working with some deformation, but you cannot too large. Too large deformation or too large crack will influence the normal surface. You see, if one grain got a very large deformation, of course no one would drive across. It's afraid to drop down. So the phase 2 is used as a base for deformation and crack propagation over the surface time. And end of phase 3 can be used as the base for calculating the loading capacity for the limited state. Because end of phase 3, that means once the load is larger than this point, the beam will going to collapse. So that's the biggest capacity for bearing force, bearing load. So this point can use as the base for calculating the loading capacity. So that means this beam, how the maximum load, how much load this beam can resist. Once the load exceeds this load, the beam will destroy. So this is the report. What's the meaning? What's the use of this report? Just through phase. Phase 1 can use to check whether this beam will working with the crack or not. And phase 2 you can check whether the crack or deformation is too large or not. And phase 3 you can use to determine the maximum load capacity, bearing capacity. So this is the 3 phases. Okay. So you haven't got this textbook.
No.
Maybe we finish the use. Can't believe or.
Actually, you should also talk to the Dawn Facebook. I'm always talking to her. She said, it's annoying. You should also try and remind them. Maybe if you say it, she'll hurry up with it.
Maybe 1 or 2 weeks ago.
Yeah, because I've been talking to her every day that the books we need it, and she said like it's nothing.
So bad.
Actually, can go.
Okay.
Yeah.
So now the whole part we see some failure mode of the flexible member. Actually, this reinforced concrete flexible member flex beam has two failure properties. One is the plastic failure or ductile failure, refer to the structure or component have significant deformation or other sign before failure. And another one is brittle failure, which refers to the structure or component have no significant deformation or other sign before failure. So, what's the meaning of these things? Have any idea? We told before.
Plastic is.
Once you put too much steel or too less reinforcement in the beam, it's not good. So only you design the beam according to your calculation and put suitable, reasonable reinforcement inside. Otherwise, the failure mode is totally different. So the first plastic failure. So which mode do you think is more dangerous? Plastic failure or the brittle failure?
Brittle.
Brittle.
Because when it's plastic, we can repair, but if it's brittle, it's sudden.
Yeah. So it happens suddenly. You have no time to reaction. So for the plastic failure, maybe you can see, the deformation is increased gradually. You can do something to strengthen it or something to repair. But for this brittle failure, it just happens suddenly, no time to do things. So it's dangerous.
But shit, I saw a hotel in Shanghai. There was built Shanghai.
Shanghai.
Yeah, they were building a hotel in the rock.
Rock?
Yeah, inside in the rock. I don't know actually in that how was they able to do it? Sure. According to the process. Is a hotel, but they build it in the carrot. How can I put it? Downstairs.
Huh?
Yeah, let me say it to you.
It's amazing.
This one. How was they able to build this one?
If it's the building is the rock. If it's the building is the rock.
It's like this. It's like this. You know? So what's the question? The question is how was they able to put it in the Oh, I see.
You see, some steel bar anchored inside the mountain rocks. Something like this. Where's the figure? This. On this wall should be some anchor. Yeah, just like something like this.
Yeah.
Yeah. Okay. So there's two different types of filaments, and for this beam with different reinforcement ratio, too much or too less reinforcement will induce different filament. You see, for this one is the properly designed reinforced beam. That means the reinforcement in this beam is calculated, not just put by experience or something like that. Yeah, it's according to the calculation of the force, and then the filament is like this. The crack, meaning the vertical crack, and the steel reaches the yield strength. The concrete or the crack reaches the compression strength. This happens at the same time. But for this second one, it's over reinforcement beam. That means you put too much steel inside. So at this situation, the steel inside have not reached its yield strength.
Okay.
Have not yet reached its yield strength, say only very small crack generated. And the reinforcement can still bear a large load, even large load, but the up part concrete have already been crashed. So that means the function of the steel reinforcement have not fully used. You just use a little part of the tensile force, tensile strength of the steel. So that means you put too much steel inside. So this filament actually belongs to the brittle filament, cutting suddenly. And the concrete was crashed suddenly. You have no time to reaction. And this one and also even this one is more dangerous. In this case, that means you will put too reinforcement inside, too small, or even no reinforcement inside. You see, in some cases, actually, in the early stage of China, some of the worker, if they want to steal money, save money, they even don't put steel reinforcement inside. They just put some bamboo inside.
Oh, what?
Bamboo.
Bamboo.
Can't believe it. Unbelievable. So just like this. What's happened? Just suddenly break down. So that means the tensile force, the capacity to resist the tensile force is very low. So that means inside you got too less reinforcement inside, or even no reinforcement inside. So once the tensile force larger than the tensile strength of the concrete, then this beam will break. Because we know the tensile strength of the concrete is very low, the compression strength is very high. So once the tensile force larger than the tensile strength of the concrete, it break. So that means this happens suddenly, even dangerous than this one, I think. Because see, this one is brick, is totally brick. But this one maybe at least the inside have much reinforcement inside.
Yeah.
This one will not break, just maybe the concrete crash and some large deformation. But this one will just fall down. So that's the 3D situation. And this one, over reinforcement and under reinforcement all belong to the brittle failure. And this one, appropriate reinforcement belong to the plastic failure. So different reinforcement ratio led to different failure moods. So based on the experimental testing, failure mood of the reinforcement concrete beam is dependent on the reinforcement ratio rule. Steel strength grade and concrete strength grade. For the commonly used hot rolled steel and ordinary concrete, the mean failure mood is affected by the reinforcement ratio. Yeah, see here, they mention that not only the reinforcement ratio, but also the steel reinforcement, or steel strength and the concrete strength. Yeah, if you use super strong concrete, maybe the situation is a little bit different. Because now some of the concrete strength can reach maybe just like the steel, like some steel, very high grade. Normal concrete was only C40, C50, and now maybe C120, something like this. The strength is very high. So, but for the normal situation, it's mainly affected by the reinforcement ratio. Therefore, in according with the steel reinforcement in concrete beam and the corresponding failure characteristics, it is expected that the 3 failure forms speciation were just introduced. And this is the appropriate reinforcement we have introduced. Another one, oh yes, here they introduced one of the coefficient. We just see this. Maybe the phenomenon you all know, but some of the coefficient we better to see. The tensile strength, this tensile steel reinforcement of beam firstly reaches its yield strength, and the stress remains stable while the strain increases significantly until the compression strain of the concrete edge of the compression zone reaches its limit. So, first, at the end of the second phase, the steel reaches its yield strength, but the concrete in the compression zone have not reached its compression strength. So that means the steel reaches yield strength first, and then the stress of the concrete increase until the compression strain of the concrete at the edge reaches the limit. That means it reaches the compression strength. And the longitudinal and horizontal crack in compression zone appear, and then concrete cracks. Before failure of the beam, crack of the beam propagates rapidly with a large deformation, and the cross section of the beam has a great plastic deformation. Then the beam has a obvious sign for damage, and there is a plastic failure. So here he introduced one of the factor or coefficient factor, this phi, the section curvature phi. So you know the curvature, section curvature. This is section curvature is an indicator of the comprehensive strength, stiffness, and deformation capacity. Its impression is this phi equal to epsilon c divided by c I h0. Is this one? Phi equal to this epsilon c divided by H0. So what's the meaning of this symbol? Epsilon C
Compressed stream.
is the strength of the concrete. And H0 is the effective height. And Kc, what's the meaning Kc?
Compression height.
Relative compression height. Relatively compression height. Height. Well, the deeper the pressure zone is Kc multiply H0. So that means to use this symbol, if this network, this distance, they use Kc B0, this distance, the compression height. And the where is the section curvature when still yield. See, this use this symbol way, fair way, corresponding to the yield when still yield. And the fair U is the ultimate curvature. So that means the beam, the deformation of the beam is something like this, or even large deformation. So maybe at this stage, this curvature fairway, and when is the curvature is a fair U. This is the ultimate, nearly is going to break, fall down. And this line is just only the still reaches the yield strength. And this stage, the beam was going to be destroyed, fall down. So different. And see, at this stage, the beam, the curvature line is developing
cracks.
Yeah. So compare with these two curves, you see, this fairway is this curve, and the fair U is this curve, the curvature. So that means makes fair U much greater than fairway. That's to see high value fair U minus fairway indicated lower component stiffness resulting in deformation increase, but better ability to bearing deformation. This is called ductility. Ductility is an important factor for component bearing earthquake and impact force load. So, another question. For this value, fair U minus fairway indicates lower component stiffness, because that means this beam is easy to deformation. But that also indicates this beam have a very good capacity for the deformation. So that beam will work in this ductility. This is called ductility. Ductility.
Yeah.
Yes. No one can breathe.
Not very much.
So yes, here is correct. Because this thing is not talking about the over reinforcement. Actually, it's just the introduction of the maximum reinforcement ratio.
Okay.
But this maximum reinforcement ratio is not to say is the largest reinforcement ratio for the appropriately designed beam. Or in other words, the reinforcement ratio cannot larger than this value. Once larger than this value means it's an over reinforcement beam. Yeah, it's the mean of this sentence. So when the actual reinforcement ratio larger than rho max, then the compressing concrete of the beam is crushed, while the tensile stress steel reinforcement have not yet reached its yield strength. Before failure, deflection and the section curvature of the beam have no obvious turning point. The crack intensity is not wide and its tension is not high. There is no obvious warning sign of failure. So it happens suddenly, not a very obvious sign of failure. Damage happens suddenly, and it's a brittle failure. This failure is also called over reinforcement beam failure. So that's this over reinforcement. So here, actually, rho max is the limit boundary. Yeah. So you cannot larger than this value. So the failure of the over reinforcement beam is to use up the concrete compressing strength, and the tensile strength still have not been fully used. Therefore, MU U means ultimate before destroy the largest load, largest moment. MU corresponding to the failure of the over reinforcement beam is independent on steel reinforcement, but dependent on the concrete compressive stress. So for this region, the loading carrying capacity actually is dependent on the concrete strength. No matter what steel you use, because you put too much steel inside. And the key point is the compression strength of concrete, not the tensile strength of steel. Because this failure is the crash of the concrete, not the steel reaches the yield. So that's the key point for this over reinforcement beam. It's dependent on the concrete compression strength. Under reinforcement beam, the rho is too small. It is also brittle failure. We said is more dangerous. So when the reinforcement ratio of the beam is small, after beam tensile concrete crack, steel stress is close to its yield strength. So once the crack appears, then suddenly the steel reaches the yield. Crack moment M crack is close to the moment M yield, corresponding to the tensile steel yielding. That means phase 2 is shorter. So phase 2 actually is the phase of the development of the crack. Crack become wider and longer. For this situation, this phase 2 is becoming very shorter. Once the crack appears, the steel just reaches the yield strength. So the phase 2 is compressed to very shorter. Normally, once the crack appears and along very long distance, where this phase 2, the steel reaches the yield strength. They have a phase of relatively long. Yeah. But now, once the crack appears, suddenly the steel reaches the yield strength. The phase 2 could become very, very shorter. Yes. So that's the difference with this over-reinforcement beam. Over-reinforcement beam is the third phase. Third phase just become shorter. Oh no. Actually, the two over-reinforcement actually is not the two. It's both of this. The steel have not reached its yield strength, but the concrete crash.
Oh, it hasn't reached its yielding strength, but it still cracks.
Yeah. It is phase 2. Is phase 2. Phase 2 become very shorter. Yes. Phase 3 become very shorter. So for this.
So the over-reinforced beam is phase 3.
Yeah, you see, we see this figure. Which one? Go back. This one. So this one is phase 2, and this phase 3. For the over-reinforcement beam, actually the steel have not reached its yield strength. It will still go up, but when it's going up, the concrete already cracked. So actually, for the over-reinforcement beam, actually there's no phase 3. Phase 3 means the reinforcement reaches the yield strength. The stress of the reinforcement no longer increase, but the strength of the reinforcement increase greatly. So for the over-reinforcement beam, the curve is like this, going up, but maybe just going a little bit, just crash. There's no the increase of the strain of the steel bar. But for the under-reinforcement beam, this phase 2, we know at the end of the phase 1 is the limit state for the crack. Once the load is larger at this point, the crack is going to appear. But for the under-reinforcement beam, once the crack appears, suddenly the steel reaches the yield strength. That means just like this, suddenly go higher and then going to phase 3. The phase 2 is compared to here, maybe just a very, very short one, very short distance. Because once the crack appears, the steel just yield, something like this.
So the under-reinforced beam can also be said to be a phase 2. The under-reinforced.
Yeah.
That one also happened in phase 2.
Under-reinforcement actually is mainly because the phase 2 was reduced or become very shorter. But over reinforcement actually is phase 3. Actually, there's no phase 3 for over reinforcement because they still have not reached the yield strength.
Can we say that the ratio of reinforcement ratio of the appropriate reinforcement is larger than minimum reinforcement and is less than maximum?
Yeah.
It's between
Yeah.
that space.
Yes.
And we can say that the over reinforcement, the ratio is larger than max.
Yes.
And for the reinforcement, the ratio is less
Small.
than the
Yes.
minimum.
Yes. So for this under reinforcement beam, when the actual reinforcement ratio is smaller than this rho mean, once beam tension crack, concrete crack, tensile strength reaches yielding strength, and then steel stress quickly into the strengthening phase, and through the yielding platform, and there's only a concentrated crack in beam. So only one crack, very light crack, just has to fall down. So crack is wide and developed to a certain height along the beam. At the same time, the compressing concrete have not been crashed. However, crack is very wide and the deformation is very small. Deflection is very small. Steel reinforcement is even pulled off. As the beam fails suddenly, it's a brittle failure. Beam that behavior this way is called under reinforcement beam. Flexion for the carrying capacity of under reinforcement beam depends on the tensile strength of concrete, and rigid unit is not allowed to be used. So you see, for the under reinforcement beam, it depends on tensile strength of the concrete. For the over reinforcement, it depends on compressed stress of the concrete. Both of these have no relation with the strength of the steel. So this under reinforcement is related to the tensile strength of concrete. Over reinforcement is related to the compressed strength of concrete. So in summary, the failure characteristic of a normal cross-section of the flex member vary with the reinforcement ratio. The feature is, when reinforcement ratio is too small, the concrete failure strength depends on the concrete tensile strength, and the cross-section size of the failure appear brittle. And B, for excessive reinforcement, the reinforcement cannot be fully used. The component failure strength depends on the size of the compressive strength of the concrete and the cross-section size. And the failure also appear brittle. Reasonable amount of the reinforcement bar should be in a range of 2 limits. And so failure of the over reinforcement and the under reinforcement can be avoided. So that means larger than the rho mean, smaller than rho max, as you said. Yes. So that's this three, actually it's two different failure modes. One is brittle, one is the plastic, for different reinforcement ratio. Okay. So the fourth part of this chapter 3 basic calculation principle of the loading capacity of normal section of the flexural member. In this, including 4-part content, basic assumption and the equivalent rectangular stress block or concrete in compression zone. What does this mean? We see in the compression zone, the stress is in curve. But in curve, it's very difficult to calculate the total force. You need to use the mathematical method to use it. How to say this thing?
Integration.
Oh, integrate, yes, integrate. Yes. Integral, yes, integral. So it's difficult.
Yeah.
So we want to make a very relatively easy method. Use the equivalent. Use the equivalent method. Rectangular equivalent. Keep this result force unchanged and the anchoring point unchanged. Keep this the value of the force and the anchoring point of the force unchanged. Then we use this rectangular shape to replace this curve. So that's means the second part, equivalent rectangular stress block. And the third part is the relative bound height for the compression zone and the medium reinforcement ratio. So we see the first assumption, plane section assumption. Actually, we have used before plane section assumption. And all level of load, the average strain of the cross section keeps a straight line distribution. So in this direction, the strain is like this. The chain is a straight line. That's it. Straight line. What's the mean straight line? That means the point to the distance of the point to the neutral axis. If the distance is larger, the strain is larger. The relation is just proportional. It's not a curve. If it's something like this curve, it's not a
Proportional.
yeah. So it's a straight relation with the distance. So it's a keep a straight line distribution, and the strain or end point on cross section is proportional to the distance between the point and the neutral axis. So that's the most important idea of this plane section assumption. And this assumption is approximate, but the error resulting from this assumption is small, so it's enough for real protection. Sorry, okay. 懂了。很急吗？很急吗？我在上课。Assumption is approximate, but the error resulting from the assumption is small, so it fully meets the requirement for engineering calculation. So plane section assumption provide the geometrical deformation of the flexural capacity of the reinforcement concrete beam and can enhance the logical and rational calculation method. This results in that formula O covers a more clear physical meaning. So which this calculation and the formula is very easy to understand and easy to calculation. And the second assumption is no consideration of concrete tensile strength. So as the correct section, most tensile concrete have not worked, but actually in real situation, still have a small part of the concrete can resist some tensile force. But in this assumption, consider the tensile stress is small, and the arm with the internal force are also small. So, hence the internal moment is small too. Then is a contribution calculation. This contribution to the calculation can be neglected, and thus simplify the calculation procedure. This means that we didn't consider the tensile force resisted by the concrete once the beam cracked. That means for this beam, once the crack appears, actually, because still some part of this concrete can resist some tensile force. But this tensile force resisted by the concrete, actually, the value is small, and also the arm of the force to the nucleus is very shorter. Then the moment generated in this part force is relatively smaller. So we just neglected because actually even you want to calculate this force, it's hard.
So insignificant.
Yeah. So we just to consider it. Yeah, just neglect it. And the third part, this summary is the sigma and epsilon curve. Because we know for the real situation, the sigma and epsilon curve of the steel is like this. For the concrete, is something like this. But for those curves, it's very hard to use for the calculation. Then, for simplify, for the concrete, the stress strain curve of the concrete have a difficult schema, and the curve considered the parabolic curve, and the horizontal line is widely used. It's like this. And this first part is used parabolic, and the end is used the horizontal line. So if they did consider this decreased part, just use the horizontal line. So make it simple. So use this formula. When the epsilon smaller than epsilon 0, normally this epsilon 0 equal to 0.002. Epsilon 0. So the ascending section, OA is a parabola, this part, and the second part, AB, is a horizontal. So where this sigma 0 is the peak stress and is taken as 0.585 FCK. FCK is the standard cylinder compressive stress of concrete. And 0.85 is the reduction factor. Meanwhile, epsilon 0 equal to 0.002 is the strain of the concrete compressing to the peak stress. This point, this stress, this sigma 0 and this epsilon 0. The strain of the B point here is the epsilon. CGU actually is the ultimate. That means that once is a strain larger than that, the structure already destroyed. Yeah. This value is equal to 0.0035. Normally we use this value. And epsilon CU is the concrete strain corresponding to the peak stress. So for the steel reinforcement, sigma epsilon relation curve, this model uses the simplified ideal elastoplastic stress-strain relation, this figure. So it's more simple. One is the oblique strain, straight line, and then horizontal straight line. The OA section is the elastic piece, and the reinforced stress of the A point corresponding to the yielding strength sigma y, and the corresponding strain is the yielding stress sigma epsilon y, and the slope OA line is the elastic modulus. AD section is the plastic stage, and the B point corresponding to the strain of the start strain or the strengthening segment sigma epsilon k. From this figure, the stress strain relation use this formula. So it's very simple, just like this. So this slope is the modulus E. And then the third part, yeah.
Actually, is it necessary to? Is it necessary to remember all these formulas?
What do you mean?
Is it necessary to remember all these formulas?
Yes.
Is it like necessary to remind her to keep it in her head?
Actually, no. You can find it in the code or in book. Actually, you don't need to remember this. Once you use it, you want to use it, just check the code or some of the specification.
So you don't need to use it.
But if you can remember, it's better.
Actually, maybe it's not so tough.
Okay. So we come to this equivalent rectangular stress block or concrete in compression zone. As we said, the real distribution is like this curve, but it's very difficult to calculate. We need to use the integral, yes. But now we want to make it simple. So the premise of the calculation flexor capacity MU or the BC RC beam is to know the concrete compressive stress diffusion with the stress failure, especially capture the force of C and the position of this force C and the position. So because it's a curve and it's changed with the distance, so it's very difficult to get to this value. So how to get this thing? When RC beam damage, concrete compressive stress distribution is similar to the concrete stress strain curve in compression. And the model in figure 619 is taken as a concrete stress curve model, namely just now we introduced it. So you type, you can speak. Maybe we have a purpose.
Yeah.
Smaller than equal to 0, the strain, the sigma, the stress, we can use this formula.
It's not
when it's larger than equal to 0, the stress equal to sigma 0. So we use this formula to calculation. The distance between point 0 and the natural x is y0 is this. y0 is this distance between the new tracks and this point. So this is between port 0 and the new tracks. We use y0, this value. See, y0 means this point 0.002, and below under this point, the stress sigma equal to this. We use this formula. Once the epsilon larger than epsilon 0, larger than this point, this part say we use this constant value sigma 0. Once the epsilon larger than epsilon 0, sigma equal to sigma 0, this value. Then, if we want to calculate the force, the C, we need to do this integrate, just like this. From 0 to this CCH0. CCH0, what's CCH0? CCH0 is the height of the compression zone. But this compression zone, the height of the compression zone can divide into two parts. One part is this curve, one part is this constant value. So for this integral, we divided this into two parts, from 0 to y0, and from y0 to CH0. Y0 is this curve, the top point of the curve. Up to this point is a constant value. So when we want to calculate the force C, the total compressive force, use this integral, and this range will divide into two parts, 0 to y0 and y0 to the top. So at this part, the stress distribution is a curve. So we use this formula, and in this part, the compressive stress is constant. So we use this value. So once you use this formula, you can go to this force C. So looks very complicated, a little bit difficult to get this value. So do you know how to calculate this? To this integral? You have to ask this person.
How should we calculate that? D, that means distance, right?
Like which one?
D.
D. Where is D?
Distance.
D?
Yeah.
No, this is the actually this is
the formula.
No. How to say? Something like this, and up point is a straight line. So this point is y0. This point is CH0. And CH0. So suppose the force action point is here, C. We need to calculate total force. So how to do this? Actually, the integrate. What's the integrate? Say we can divide this figure into many very short parts. So suppose we take this short part. The height of this short part
D.
is a dy. The height is dy, and it's just like this. This rectangular height is a dy, and the width is this. Width is this sigma epsilon b. B because the beam, the width is b, and at this point, this means like this. Sigma epsilon means the stress value on this part point at this area, the force equal to B multiplied dy is the area. Area this part. You know the area, you know the stress, sigma epsilon, then multiply this. Then this part is the force in this small part area. And for other part, something like this, let's make this integrate.
Okay.
Something like this, actually it's like the sigma. You divide it into many small parts, and that's the sigma together. Actually, integrate it equal to sigma. I think this is, it should be learned at the first year. Okay. So actually, there's many methods of technique to do this integration. It's a little bit complicated. Yeah. So finally, you can got C. If you do this integrate, finally you can got C equal to this. This is the result.
Yes, gotcha.
So if you ask why this, then you should do this integrate. Then you can find that the result is that. Okay. So the where C is the distance from the location of the force C to the edge of the compression zone, and the chemical calculation is where C. Where C is this point, action point. This part from the distance from the location of the force to the edge of the compression zone. This part where C. So where C equal to this sigma, cos C is 0. Cos C is 0 equal to is this the total height of the compression zone, and where C is this part. So this part, this value is the point, actually point of the force to the neutral axis. You see, this integral, what's the difference with the former one? You see this one, from 0 to cos CH0 and sigma B dy. And here you see, also from 0 to sigma, but here
dy to dy.
Another way. Because use this formula the result is C. This formula, the result
Is the inverse of C. This times C.
is C plus y, not yc, is plus here this distance we see this distance. It's actually like a area movement because another way, or it's just movement because if there's no y, the result is actually the force. Force multiplied by actually is the arm. It's the movement. The result is the movement. So this is the up part of this is the movement of this real distribution force to the nucleus. And divided by the result of the force, then we can go to the action point of this force. That means the movement, actually the movement induced by the compressive force to the nucleus keep it unchanged. Then we can find the action point. So, any question for this formula? For this formula, the key point is to find the action point of this force C, compression force C. This is the distribution force, but the result force or the total what's this word? Okay, what's this word? Okay, this name is curly. So for this formula, the purpose is to get this action point or the compression force. Which one do you use for this force? The resultant compression force or the
Resultant force.
You can use this one? Okay. So through this formula, we can get the action point for this compression force C. Then got this value, then we know this YC, the action point to the edge of the compression zone. So this YC equal to this, just change this, move this, because you see H0 outside from this formula, then and do this integral. Finally, you find this result is like this. It looks so complicated. So basically, using this concrete compressive stress strain curve to compute the force C and the location C is not easy. It's so complicated. But actually, you see, in this formula, actually, it's simple. Only this sigma equals 0 equals CU, and also CC. Only this three symbol is
Must be.
you need to know. Another just value.
And H0.
H0, actually H0, yeah. Normally we know the height of the second H. And the H0 normal equal to H minus AS. And the AS what I said last time, normally is the center of the reinforcement to the S. The center or if many layers is the central of this to the edge. Normally, AS we don't know. At the beginning, we normally just make assumption. Suppose AS equal to 50 or 45 or something like this. If it just one layer, something like this. If two layer, maybe just 16 something. So a simplified method that uses the equivalent rectangular stress block or concrete instead of the actual diagram is used. So how to do this equivalent rectangular block? So use this equivalent rectangular stress block concrete instead of this real actual stress diagram must satisfy these two following conditions. Is this: keep the position of the force unchanged, and keep the sign of the force unchanged. The value and the position cannot be changed. This is the basic things. Then, how to do these things? Here, introduce the two dimensionless parameters, bed and the gum. Bed equal to x divided by xc, gamma divided by sigma divided by sigma 0. So we introduce the two new symbol. Then from figure 390 is this figure. We can see the force C equal to gamma sigma 0. Gamma sigma 0 equal to the real sigma, and B is less, X is the height we need to calculation. The height of this equivalent rectangular stress block. And then if we use XC, because here we see here bed equal to x divided by XC, then replace this is me like this. And then the action point of the force C, where C, because where C, if we use the equivalent rectangular block, of course the action point should be in the middle of the block. So it should be x divided by 2, half of the x. In the middle, because you use this equivalent rectangular shape, the action point, of course, in the middle. So equal to x divided by 2 equal to back xc divided by 2. Because over here we suppose this x equal to back divided by 2. Then we just replace this thing into this. We can go to back. Finally, we can go to back equal to those things.
Okay.
And gamma equal to this. So when determining epsilon 0 and epsilon 0, the equivalent rectangular stress block of the compression will replace the actual stress block in this figure C. So because in this formula C, the only thing we don't know is sigma 0 and sigma CU. If we know these two values, then we can go to beta. Once we know beta, then gamma we also know. So that means if we know this two value in this formula, for this real distribution, we can use this rectangular block to replace it. So So normally, if we're taking epsilon 0 equal to this 0.02, come with the ultimate compressive strain equal to this 0.0035. Then from this equation we can get got beta equal to 0.8095. The height equivalent stress block x equal to this, and the equivalent stress value we got this. You see, the key point is epsilon 0 and epsilon cu. Once we determine these two values, the equivalent block, you just know the x and the value. So for the ultimate compressive stress Cu, sigma Cu, the corresponding coefficient beta of the edge of the compressive concrete of flex member in this code specify this value based on the concrete strength listed in table. The equivalent rectangular stress book for the compressive concrete combined with the experiment date at home and abroad. This code takes the equivalent rectangular stress value gamma sigma 0 as FCD, and which FD is the actual compressive stress. Then got this in the code. We got this table because we see this beta and the gamma all based on this epsilon 0, epsilon cu. Actually, epsilon 0, epsilon cu only related to the grade of the concrete. Different grade of concrete will have different value of this epsilon 0 and epsilon cu. Then in this block, in this code, C50 and below, they use this value. And C55, 60, 65, so gradually getting smaller. And once we got this value, you can got this value. See here, they use this 0.8. Actually, just now we got 0.8095. They just neglect those parts and use this 0.8. So this value you can find in the code. Once you determine what concrete you use, it will be C50 or C60, then you can directly go to the value of the beta. Once you know beta, what do you know? That means you know the distribution of the equivalent rectangular blocks. Once you know beta, then you know the x, because x equal to beta xc. And once you know beta, then you got this gamma. Once you know gamma, then you know the x is stress, equivalent stress. So that's the why the value or the value beta in this table, how we got this value. So because we check the code, it does tell you how this value come from. But now we just tell you how we got this different grade concrete have different values of beta. Just use this equivalent rectangular stress block and use this formula, then you can got this beta value.
Laoshi, when we start to design, we will just add the formula and we will not need to calculate the value. In the code, we will find the value.
Which value is it?
For example, the value of beta.
Yeah.
We just see if, for example, I have to calculate something. I have to calculate the strength of a pin or something like that, and I'm finding that I need to calculate the C, for example.
Yeah.
So the better I know the formula, I will know the formula, I know the kind of material I will use. So how to know those values? I will find it in the code, or I will find it.
Yeah, you can find in code.
So I will not need to calculate them, but the value are always there.
Yeah.
I will just need to apply.
Yeah.
Okay. So this is the only things we do.
Yeah. This tell you how does this value come from.
Okay. Okay.
But you can know this value directly from the code.
Okay.
So different grade of the concrete have different value of the bed. And from this figure, you see different value means different of the film. Actually, for this slope line AC is appropriately defined redefined reinforcement. Actually, is wrong. And for this in the middle AB is the limit situation, limit boundary for the reinforcement. And once for this AB line means over reinforcement situation. You see, for AB situation, CB H0, this is the compression zone, the height of the compression zone. Once the compression zone is larger than this value, that means it's over reinforcement. Once the compression zone, the height of the compression zone is smaller than this value, is appropriately reinforcement. Actually, it cannot be too small. If too small, that means under reinforcement issue. But in this figure, only tell you the boundary or the over and the appropriately reinforcement. Just this CB. This point.
For the enemy reinforcement B,
What's your? Yeah. Follow here. We just reduce this. So this boundary failure is that the tensor. So for this AB line, CB H0, if the compression zone, the height is like this, that's the boundary failure. At this point, the tensor reinforcement reaches the yield strain sigma y. See here, or epsilon y. This from the B point to this point, the length equal to epsilon y. This epsilon y is the yielding strain of the reinforcement. And begin to yield, and meanwhile the compressive concrete zone also reaches the ultimate compressive stress epsilon Cu. See, at this point, the 8 point, the epsilon Cu of the concrete. Epsilon Cu is the strain of the concrete, and this epsilon y is the strain of the reinforcement.
So epsilon Cu is the for the concrete.
Yeah, because of this up part is in compression zone, the lower part is in tension zone. So at this situation, the height of the compression zone, X xb equal to kcb h0. So this height. So at this AB, this line, at this region, the concrete reaches the ultimate strain, and the steel reaches the yield strain. So having at the same time, that means if this condition is the boundary condition, this happened at the same time, not the steel reach the yield strength, and the concrete have not yet reached the compressive stress. At this situation, at this point, the concrete reaches the compressive strength. The reinforcement reaches the yield strength, happening at the same time. So that's the boundary. Once the reinforcement is smaller than this, or become like this AC line, the strain of the steel actually is development large, is larger than epsilon y.
It's S.
Is this?
Yes. It's
No, X Y is greater than X.
so
Or you talking about the AC? For the AC? For the AC.
Yeah, for the AC. For AC, it's appropriately reinforcement.
So now epsilon y is that we can say that epsilon y can be like the maximum version for reinforcement.
What's your mean?
In the appropriate reinforcement beam damage,
Yeah.
the fellow is plastic, right?
Yeah.
So it's the same way when we talk about the ratio. We say that the ratio
Yeah.
must be less
Actually,
or equal.
for AB line, is the ratio is the maximum, rule maximum.
Okay.
That's the boundary of the reinforcement ratio.
Okay. So for appropriate is less. It must be
Yeah.
less. But here, according to the MC, but the epsilon has to be bigger.
So the failure of the under reinforcement concrete flex member begins the yielding tensile strength, and after the period of deformation strength, concrete strength at the member field. And this one, actually this one is wrong. Actually, it's not under reinforcement. Actually, it's appropriate reinforcement. This one is wrong. And the member field at the same time the tensile strength of the tensile reinforcement satisfy this value, and so strain distribution of the appropriately actually I don't know. This figure cannot. Some people just took this picture. Okay. So the strain distribution of the appropriate reinforcement beam is the AC line. Figure at this time the height of the cruising is smaller. Axis is smaller than say. This compression height is smaller than this height.
Yeah.
And the failure of the over-reinforcement concrete flex member began that the concrete spring reach ultimate spring, the member field, because for the over reinforcement, it depends on the compressive stress of the concrete. At this time, the tensile strain of the reinforcement is less than yield strain, and so strain distribution of the over reinforcement beam is the AD line. The strain of the steel is smaller than epsilon y. Yeah, because it's too much steel inside, and currently reaches the yield strength. So it's seen from figure 20, boundary damage is the boundary of the over reinforcement and the proper reinforcement concrete. With the actual cross-section height of the compression zone XC larger than this value, it is the over reinforcement beam. Is this? If the XC larger than this CB is 0, that means it's an over reinforcement. When XC is smaller than this, is appropriate reinforcement. Here is also wrong. Therefore, this CB equal to XB divided by H0 is used as the boundary condition. CB is used as the boundary condition. Where XB is the height of the concrete compression zone when boundary failure occurs, depending from the plane section assumption. So we can use XC compared with, or use the CB, the CC compared with the CB. Say, if CC is smaller than CB, that means it's appropriate reinforcement. If CC larger than CB, it's become an over reinforcement. See this? X equal to CC and multiply H0. CB is the boundary area. Once CC larger than CB, it's become over reinforcement. Once CC smaller than CB, it's normally it's appropriately reinforcement. Of course, we have another minimum. It should be larger than the minimum reinforcement ratio. Yeah, just this region from this point to some point of this. So call this CB as the boundary condition. For the limit height of the compression zone of the equivalent rectangular stress distribution, because we know this, the compression CB should be X divided by H0 and use this value. And by the geometry relation, okay, a break. So you see this, the boundary condition is CB, you can calculate it by this, then XB divided by H0. So now XB divided by H0, we can replace it by this. From this geometry, we see XB divided by 0. Why we can use this? We see this figure. XB divided by H0. So this actually this xb cb multiply h0 equal to xb, and h0 is this. So xb divided by h0 equal to what? Here, xb divided by h0 equal to epsilon cu divided by cu plus epsilon y. So y. So this point.
But actually, what is AC?
xb.
Yes.
Actually, I will figure. Suppose this sheet is CB, CY, and this C, this is U. Is C, which is S. So this distance H0, and for this A C B E, this distance xb equal to cb h0. The compressive height for the boundary condition. So now we xb divided by h0 equal to cu plus where? It is where?
No, it's plus HCl.
Where?
No, it's not one.
So why? XB, this is XB, this distance is H0. So y xb divided by h0 equal to epsilon cu, this epsilon cu plus epsilon y. That means this distance plus this distance. Is it? So y this divided by this equal to this divided by this plus this. How can I get this result? See.
I think maybe actually from their formulas, maybe the formula of ASP and the A0.
Oh, we just change. And in what is going to be this H0 divided by xb equal to sigma cu plus sigma y divided by sigma cu.
Less.
So we can write H0 actually equal to this xb plus, suppose we see this part is xc, something like this. So H0 equal to xb plus xc. Then here xb plus xc, this one, and this one. Finally, is xc divided by xb equal to epsilon y by epsilon cu. So xc is this distance, and xb is distance. Epsilon y is this distance. Epsilon u is this distance. Because these two angles, is similar. What's the relationship? Yeah, proportion. So xc divided by xb equal to epsilon y divided by xu. So one way we can call this, that xb divided by h0. Actually, we can use epsilon cu divided by epsilon cu plus epsilon y, because in this, the purpose of this, our purpose is to get Cb, but Cb equal to xb divided by h0. So we need to find the value for xb divided by h0. Then we can, because xb actually is difficult, so we can use this epsilon cu, epsilon y to get xb divided by h0. Then we can replace xb divided by 0 by this. Then finally we can get Cb. So this got a little bit, yeah. But if you just decompose this,
That's what we said, the plane section assumption.
yeah. Plane section assumption, that means the straight line is straight. The strain is a straight distribution. So finally we can replace, we got this Cb. Because in this formula actually say back, you can find in the code. Epsilon cu, epsilon y, actually it's depends on the material. So that means we don't need to calculate xb, we don't need to calculate the real height of the compression zone. We can get this Cb, the boundary condition with Cb. Actually, Cb means that xb is just a non-dimension. It's an xb divided by h0. It's a non-dimension coefficient. The real name is a relative compression height. It's something like this. The limit height compression. I remember this better. What's the better name? Something. I remember something is called like this. Yeah, something like this. So we know Cb we can got by this value plus by beta. So substitute xb and sigma y into formula, the boundary height for the compression zone. You can got this value. You see, they replace the epsilon y by this, because SD is the standard tensor strength of the reinforcement, and the E is the modulus. So we can replace each way by this. Then finally, KCB, we can use this formula. This is the base to determine the height of the concrete resolution. Actually, KCB you also can find directly in the code.
Really?
Yeah. Here.
Why the strings?
So this is just tell you how
To get it.
yes. So in the table, in the code, you got the table different code, different grade of the concrete, different grade of the reinforcement. You got a different value of the KCB.
Stress.
But you
He's right. It's better to understand how. So before we run it, we thinking about which number, how they get that number in the first level. And now you.
It's necessary to even know the formula. It's like they are already fixed values.
yeah, but if you just see the code, see this value, you don't know how they come. Yeah. You should know how to calculate this. So once you determine what material, what's the concrete, what's the reinforcement they use, then you know the boundary condition of the KCB. Okay, normally it's just around 0.5. 重量要 material, the concrete, the reinforcement. And then the medium reinforcement ratio. For this boundary condition, is the maximum reinforcement ratio. And we should, for the appropriate reinforcement design, below it should smaller than maximum reinforcement ratio and larger than the medium reinforcement ratio. So how to get this medium reinforcement ratio? So in order to avoid the film mood of the under reinforcement beam, it's needed to determine the medium reinforcement ratio. Medium reinforcement ratio is a bound of the no, he also wrong. It's actually the proper reinforcement and the under reinforcement. When the beam reinforcement ratio greatly decreases, the working characteristic of beam changes from a reinforced concrete structure to plain structure. So therefore, medium reinforcement ratio is determined by the rule that when reinforcement concrete beam fail using medium reinforcement ratio, the flexural capacity of the normal section MU is equal to the standard value of the protein moment for the plain concrete beam with the same size and the same material. So from use this value of MU to get this medium. Yeah. So based on the result from the Barb principle, taking into account the temperature change, shrinkage, stress, as well as past design experience, the general specification for highway grade and the cover to provide the medium longitudinal reinforcement ratio of flexible reinforced concrete beam. For the reinforcement on the bending side, rho minimum equal to maximum of this 0.2 and this value. FTD is the tensile strength for the should be the tensile strength for the
Actual reinforcement rate.
yes. No. FTD is the tensile strength of the concrete. SD is the tensile strength of the reinforcement. So between these two values, use the latter one called the medium reinforcement ratio. Actually, this value is say from the experience, they consider the shrinkage and temperature is similar experience formula. It's not a theory from a theoretical. It's based on experiment and experience. So this is the 4 part of this chapter 3. This time, the 5th part, singularly reinforcement rectangular section flex member. This part is mainly tell us how to calculation, how to design the rectangular shape, rectangular section beam. Basic formula and the application condition and the calculation method. So basic formula, you see, this is the rectangular section beam, and we directly use the equivalent rectangular stress block. According to the basic principle for the flexible capacity, schematic of the calculation of the single reinforcement rectangular section of the flexor member is in this. You see, for this section, when you make the balance of the force, because in this section, you see, it goes to the tensile force, it goes to the compression force, and also it goes to the moment. So if you keep this component balanced, the tensile force and the compression force should be in balance in opposite direction, and the value should be the same. And the moment, suppose to the neutral x or to this edge or to where, the moment should be the same. Because you got tensile force, you got the compression force, to the same x or to the same point, all the force generated, the moment generated by different force should be in opposite direction, and the value should be the same. The result should be 0. The moment should be 0. Is it? Keep the component balance. So basic principle is that most adverse effect of the basic combination or load on calculated section of the flexor member should not exceed the loading capacity. So this is the design. For the figure, the basic calculation formula for the single reinforced flexor member with a rectangular cross-section can be derived using the equilibrium condition of the internal force being 0. T is tensile force, C is the compression force, should be FCD BX. FCD BX. B is the width of the section, X is the height of the equivalent rectangular stress block. So FCD is the compressing strength of the concrete. So FCD-BX is the compressive force. And T, FSD, AS. AS is the area of the reinforcement. And FSD is the tensile strength of the reinforcement. Then we go to the balance. Compressive force and tensile force, the value should be the same, but just the direction is in the opposite direction. So you keep the balance. And then for the moment, from the equilibrium condition of the sum of the moment resulting from the point of the tension reinforcement T on the second 0, the balance equation should be like this. FCD BX, the compressive force. H0 is the effective height of the section minus half of X. So that means this is the compressive force. From the compressive force to the reinforcement, this distance equal to H0 minus half X. that's the R of the compression force to the reinforcement. Then, because at this end, the movement induced by the load, the outside load, the external load, is gamma 0 md. And in this section, the resistive moment or the internal force should be large than this value.
It should be larger than
Yeah. Because you resist the force should be larger than the load force. So from the equilibrium condition of the summary moment resulting from the point of the compressing concrete force C on the section B0, the balance equation can also be written like this. The external force keep the unchanged gamma 0 md, and the moment Fsdas, the tensor force, and the action point h0 minus half x is to tensor force. The action point is here, so general moment is like this. So this moment keep balance. So now we got these three formula. One is the balance of the force. Another two is the balance for the moment. So here you see it's large or equal, at least equal.
less or equal.
Yeah, you should at least equal, especially larger than the load. The resist force larger than the load force. Yes. So where MD is the design value for the combination moment of the calculation cross section, gamma is the structural important force. Do you remember what's the value of gamma 0? Is the important factor of the structure. So what's the value of gamma 0? What have we introduced before? No idea?
The formula or the formula? Or the value?
Huh?
The formula or the value?
The value. The value. We have divided the structure into three grades.
The value
Oh,
of
we have divided. Yeah.
Very important, of normal.
equal to 1.0.
Yeah. The very important should be 1.1.
1.1.
The important 1.0. The normal structure is just 0.9. This structure important factor gamma 0. So MU is the flexural capacity of the computer section. MU, the resistor, the resistor capacity actually. FCD is the design value of concrete compression strength. FSD is the design value of the longitudinal tensile strength of steel reinforcement. AS is the cross-section area of the steel. X is the calculation height of the compression loop according to the equivalent rectangular stress. Yeah. B is the Y is the cross-section, and H0 is the effective height of the section. H0 equal to H minus AS. AS is the central of the steel bar to the surface of the beam. So this is the three formula, basic formula for calculating. The equation, these three equations are only suitable for, actually it's not, and it's an appropriate design reinforcement. It's wrong. Maybe, and the reinforcement, sometimes maybe have the meaning of appropriate reinforcement. times for this situation. Maybe it's mistake. It's not applied to the over reinforcement beam. And shit, it's mistake. Because these two words have different meaning. So some people make mistakes.
In the book?
Yeah.
The book is different.
No, this is from the early version. Now the new version have correct.
So the book that you said we should get is different.
Yeah, this book is correct. Because I haven't got the electronic version, so the PPT just use the old version. So because when the over reinforcement beam fail, the actual tensile stress doesn't reach the design value of the tensile strength. So the FCD cannot be used. Therefore, the formula applying condition is, in order to avoid the over reinforced beam, the height of the compression zone should be satisfied with, because KCB plus H0 equal to XB is the boundary condition for the, remember?
Yeah.
This XB, KCB H0. So X should be smaller than this boundary condition. Because this three formula is not suitable for over reinforcement. Once the X larger than XB is belong to over reinforcement, this formula cannot be used. Because over reinforcement beam, the steel have not reached its yield strength, tensile strength, so cannot use FSD. So where CB is the relatively limited height for the compression zone and can be referred according to the concrete strength and type of the steel parameter in the table in the code. From the equation, the calculated dips for the compression zone, X can be represented as. So this is simple. Just use this formula. X equal to remove FCDB to this side. X equal to FSDAS divided by FCDB. So that means when you know the area of the steel and the material, then you can calculate, you can got the equivalent height of the stress block. So the relative height of the compression zone, actually X and KC is the same thing actually. One is KCD is dimension, no dimension. X is just the real height, something like this. Yeah. You see, KC equal to X divided by H0. We replace X by this FSD, FCB, and AS BH0. Here, AS is the area of the reinforcement. BH0 is the area of the beam. Then AS divided by BH0 equal to rho, to the reinforcement ratio. Then you see KC equal to the ratio rho multiply SSD divided by FCD. So that means this KC is actually reflect lots of things. Not only the reinforcement ratio, but also the relation of the material strength. This is the strength of the reinforcement. This strength of the concrete. Yeah. So from this figure, we can see is not only reflect the reinforcement ratio, but also reflect the stress ratio of material. And so, KC is also called the reinforcement characteristic value. and more general meaning than this reinforcement ratio. When Kc equal to Kcb, the maximum reinforcement ratio, rho max for the appropriate reinforcement beam is. So that means from this we can calculate the reinforcement ratio. Because Kcb you can find from the code. FCD, FSD actually also can find on the code because of the strength of material. Then you can find the reinforcement ratio, the boundary condition of the reinforcement ratio. So then you know how much steel actually put inside. I cannot be more than this. So before you design, you can use this value to check if you to control the amount of the reinforcement, how much you cannot more than this. Clearly, reinforcement ratio over this actually is a proper reinforcement should be smaller than this value. And in order to avoid under reinforcement or lower reinforcement, the reinforcement ratio should also larger than the minimum value.
Oh, so that's
Smaller than max, larger than mean. Mean is this value here, this value. Okay, we'll finish this. Last class we talk about auto calculation.